So this chapter is all about work and energy. Some of these formulae you should have seen in previous physics courses, but we'll just quickly go over them. So for the potential energies, you'll use the gravitational potential energy, MGH. And for elastic, 1/2 kx squared. Kinetic energy defined to be 1/2 mv squared. And don't know what that line is. So potential energy of gravity, it all depends on how you define this height. Remember that if you define h equals 0 to be there, then h is greater than 0 if you're higher, and h is less than 0 if you're lower. Potential energy, therefore, can be positive or negative. For a spring, this potential energy elastic, it doesn't matter whether you stretch the spring away from equilibrium. So if this is x equals 0 and you stretch it, that's positive elastic potential energy that's been stored up in that spring, or you can squish it. So if 0 is here, and even if x is negative, it doesn't matter because you've got x squared, so potential energy elastic is always positive. Kinetic energy, this is speed, so this is always positive as well. Okay, now the way that energy changes from one form to the next is if some force does some kind of work. And so the definition of work is force times distance times the cosine of the angle between the two. So if you have a force acting at some particular angle theta, and the displacement is along the floor, then it's the parallel component. It's this F cos theta that's doing the work. The perpendicular component does no work. So F sine theta, this does no work because it's perpendicular to the motion. Now, the way you can decide whether something does work, positive, negative, or 0, is just think about, is the force trying to speed up the object? Doesn't matter whether it succeeds or not. If it's pulling in a direction that is trying to speed up the object, then the work is positive. If it's trying to slow down the object, usually that's friction, but it could be other forces, then the work is negative. If it's perpendicular, which means you can't either speed up or slow down something if you push perpendicular to the way it's going. So if the force is perpendicular, that means 90 degrees to the displacement. Now the thing has to move in order for work to be done. It can't just sit there. It doesn't matter how many forces are on it. If it doesn't move, there's no work done by definition. So force is perpendicular to the displacement, there's no work done. Now the thing that students have the most difficulty with, I find, is when a box is just being lifted up and down. So there is the force of gravity always. Now, if this box, and then you're going to lift it up. So this is U, Fu. Now, these two forces will both do work as the box moves up or down, but it all depends on which way the box is moving and which work you're talking about. So case 1, let's say the box moves up. Okay, so the displacement is up. Now, which of those forces is trying to speed it up and which is trying to slow it down? If it's moving up and you pull up, well, clearly that's going to try to speed it up. So U, Fu, does positive work because they're in the same direction and it's trying to speed it up. The force of gravity does negative work. Positive work, so it does negative work. You have to be really careful when you read the question. Is the question, are you doing work or is gravity doing work? And so that's completely different. Now the net work, if this thing moves at constant speed and they ask for net work, well then often it's 0 if these two are the same number, but it depends how that's moving. Okay, second case, box moves down. Okay, so now the displacement is down. Now think about which force is trying to speed it up. Gravity is trying to speed it up. And so gravity and displacement being in the same direction, now gravity does positive work. And you are holding it back. So assuming if you lower this at constant speed, you have to hang on to it so it doesn't crash to the ground with the acceleration of negative 9.8. So you, as that lowers at constant speed, that force does negative work. Okay, and if it's not moving, there's no work at all because it has to move to do work. Okay, another very useful formula is that it's called the work energy theorem. The net work done is the change in kinetic energy of the object. So this is the final kinetic energy minus the initial kinetic energy. And you have to work this out VF squared minus VI squared. You can't go VF minus VI and then square it. Now this net work, it means you have to deal with the net force times D. And this is actually a dot product. You would normally just do all the work from each individual force separately. Okay, I don't think this course deals with dot products, so maybe I shouldn't have written that down. Okay, another formula that you're going to need is power. And so power is work, the rate of doing work. It's work over time. Now, there's a number of different ways that you can write this. If this is net work, then you can say change in kinetic energy over time. If speed's not changing, but maybe the potential energy is changing, you can go change in potential energy over time. Sometimes work is force times distance over time. Sometimes you can use average force times speed. That will also give you power. Okay, so those are all going to come up in little questions that you have on Mastering Physics. The units here are watts. And a watt is a joule per second. Okay, now a couple of the questions deal with thermal energy. So when we have conservation of energy, which is a fundamental conservation principle of the universe, it basically means energy before, total energy before, equals total energy after. Now, when you're adding up the total energies, before, you're only just going to have these mechanical ones that you know about. You're going to have kinetic, initial, potential energy of gravity, potential energy of a spring, possibly. I mean, there might not be all of these. And that's going to be it for you. And there's no heat loss initially because nothing's happened yet. Now something happens. Maybe it slides across a rough floor or down a rough slide or somewhere where there's friction. As far as you're concerned, it's always going to be friction, maybe air resistance, but you're going to lose some of this energy. So maybe that equals 100 joules. But when you add up all these mechanical energies afterwards, you're going to get something less than 100 joules because you've lost it to heat. And so then this is where heat goes over here, heat. And this is a positive amount of energy. And in your textbook, I think they call this delta E thermal. And so if you add all these guys up and maybe you get 100 joules before anything happens, then something slides down a hill or crashes into a spring and compresses it, or I don't know, falls off a cliff or something. This might only be 80 joules. The loss is the 20 joules. Okay, so that's where the thermal energy goes. Now, you can calculate thermal energy from friction. If you want to do from friction, then the thermal energy is a positive number. It's the force of friction times the displacement over which the object moves. So whatever this would be the distance where there's friction. Might not be the whole distance that the thing is moving, but this is distance where friction acts. Might only be a small patch of the slope, for example, maybe, I don't know, 10 meters, it hits a rough spot. So you take the force of friction times the 10 meters, that's how much heat you would lose. Now beware, you might also read that the work done by friction is negative force of friction times distance. That's absolutely true. Friction does do negative work because it's trying to slow the object down. But the amount of heat generated, that's a positive number. So you take the absolute value of that work. Okay, so some questions that you might have will be things like objects sliding down ramps. And we've already done all the geometry of ramps. For potential energy, if there's no friction, the thing that counts is the vertical distance it falls. So that's going to be the important quantity here. You're going to have to know the vertical distance something falls. If something is moving and then squishes a spring, well, its kinetic energy then turns into the elastic energy. Okay, and there's lots of good videos on conservation of energy problems and lots of good examples in your PowerPoint slides. So that should do it.